Welcome to episode 11 in the Insight xtUML Learning Series, and thank you for joining me. My name is Dean MacArthur, and in this segment I'll be describing how time is integrated into xtUML models, and some of the pitfalls that can occur. The Insight xtUML series is sponsored by the xtUML.org community, and I encourage you to visit their site and learn more about the community. This episode is part of an ongoing series of presentations covering all aspects of xtUML modeling. If you have missed any of the earlier segments, they can be viewed using the links at either xtUML.org or on the YouTube channel that they've created. Earlier in episodes 3 and 4, the steps to creating an xtUML model were described, and the runner's GPS watch example was presented to demonstrate the steps. In these episodes, the presenter described the pieces of the model, the diagrams, and the blocks of action language that combine to form the entire system. Later in episodes 6 and 7, this model was executed and then translated into embedded C. Here the model was shown to execute, and the intended behaviors were demonstrated. Missing from these discussions were the rules that the simulator and the model compiler use to execute the models. Some might say that as long as it runs, you don't need to know or understand the rules used. However, in my experience, there's more than one way to implement a system requirement or component behavior. By understanding the rules of execution, I find architects and designers are better able to predict how a particular diagram or block of code will perform, and this leads to more efficient models in a shorter amount of time. Central to the definition of xtUML's rules of execution is the modeling of time. So while my talk today is titled as a talk about time, it is also a talk about learning these rules and learning how to harness them. To begin my talk, I will spend a few moments exploring our perception of time in the everyday world. During this exploration, some of the attributes of time that are key to system modeling will be highlighted. With these attributes, the rules of execution for xtUML models can be presented. These rules are central to becoming an xtUML modeling master. Each rule is explored in detail. Having presented the rules, I'd like to answer 3 common questions that new modelers often pose regarding time. These questions can lead to model inefficiencies and long debug efforts if you're not familiar with the rules of execution and the capabilities of your simulator. Whether observing a busy street corner, as shown here, or a conversation at a coffee shop, our eyes experience a steady stream of images. It is this progression of images that the dictionary defines as time. While that definition is very helpful to philosophers, it creates information overload for system modelers. So the first step is to recognize that an xtUML model is an abstraction of the real world, and consequently only needs to include the key attributes of time. The first attribute is clearly shown in this street scene, where numerous cars, pedestrians, and cyclists are progressing down the street. Each of these are acting independently, and there is no global mechanism that controls progress or restricts where responses can occur. So the first attribute that xtUML's rules must include is that all participants are acting independently at the same moment. Next, if we consider the cyclist in the foreground, a driver in one of the cars, or the truck driver next to the garbage truck, each of these participants will have a different perception of the scene based on their location. Consequently, their version of time, their stream of images, is unique and different for each observer. So the second attribute is that time is relative, and each participant's life cycle advances solely based on the interactions that they perceive. Looking closer, you can imagine that the drivers in each car have their eyes fixed on the brake lights of the car ahead, or the traffic lights above. As they continue to stare, they are looking for a change in the lights, possibly the activation of the brake lights or the toggling of the turn signal. The information in this exchange is not in the details of each image that appears, but in the change. These changes are examples of events, and the participants in our street scene are influencing the actions of others through events. These events are discrete and are exchanged between a sender and a recipient. Also, when the event is sent out, it can go to many recipients simultaneously. However, recall that time is relative to the observer, so each of these simultaneous events is really a sender-recipient pair. Events, while discrete, are not always independent of previous events that are sent out between the same sender-receiver pair. Consequently, a stream of events can have an order, and as we'll see later, maintaining event order across a complex system is a challenging design problem. Now at the recipient, the arrival of an event leads to internal and possibly external action. Part of that action involves analysis, decision-making, and then possibly a reaction. In all cases, the recipient has changed their internal state. The challenge is to find a set of rules that describe this event-oriented model of time, that permits each participant to be active concurrently, and that communicates using an ordered series of events between sender-receiver pairs. For xtUML, the rules of execution that have emerged are captured as part of Stephen Meller and Mark Balker's book, Executable UML, A Foundation for Model-Driven Architecture. This book is the master reference for executable and translatable UML. And in Chapter 11 is included an expanded discussion of the rules of execution. As was shown in earlier episodes, the xtUML executable model starts with a component diagram which describes the partitioning of the application and the interfaces that exchange messages between components. To describe the activities within a component involves 3 layers of detail. At the outer layer, a class diagram which shows data members of each class, operations to be performed on the data members, and associations between the classes. Next, inside each class, functional or data processing details are expressed in state machine diagrams and functions. Then, at the most detailed layer, are blocks of action language. These blocks describe procedural steps that must be performed by the function, operation, or state within a state machine. Once all 3 layers have been completed, then a behavior can be considered implemented. Under the xtUML rules of execution, a simulation is split into a system assembly phase and a dynamic execution phase. During the system assembly phase, the top-level system component diagram is considered to be defined to be a static structure that is established prior to the arrival of the first event. During assembly, empty component shells are created and then interconnected using the interface definitions documented in the executable model. Once the structure of the components and connected interfaces is fully established, execution switches to the dynamic phase. It is during the dynamic phase that action language will be executed to create and then relate the instance population within each component. At the start of dynamic execution, a block of action language is selected by the test configuration to begin the process of establishing an instance population and creating events that will drive the remainder of the execution. From this starting point, the xtUML rules advance time according to a mixture of events generated and the composition of the recipient's lifecycle. Eventually, all events are processed, and at that moment, dynamic execution concludes. For individual instances in the population, they are created according to the class definition, including the state machine that defines its lifecycle. Each instance has its own lifecycle state machine, and all state machines execute concurrently. In this way, the xtUML execution rules implement the independence and concurrency that we saw earlier in the traffic scene. An important implication of permitting each instance to advance along its lifecycle in this way is that time becomes relative for each instance, and that the rate of advancement is governed by the order that events are received. This dependency creates a need for architects and designers to be mindful of local synchronization when events are sent. For a message sequence that involves a request followed by a response between two instances, then the pairwise nature of the interface definition ensures that relative to each other, time progresses in the proper order. Even if the processing time for a given state were to vary, the sending of subsequent events are also delayed, and the order of state executions within each instance is maintained. So for this type of communication, where it's between two instance pairs, events are sufficient to maintain synchronization. The two life cycles will be synchronized during the exchange. However, when more than two instances become involved in the progression of an instance along its life cycle, greater care is required. In this example, I am showing three instances, where events arriving from classes on the outside are used to advance the life cycle of the central instance. If correct operation matches the pattern shown, what happens when the instances on the right side advance at a faster rate? In this case, the left and middle instances are maintaining their relative timing, but that cannot be said for the middle and left instance pair. When synchronization is lost, the model's behavior can be unpredictable. Another way to look at this aspect of the execution rules is through a simple sequence diagram. Here, I will only look at the case where three instances are involved. In this example, instance A sends two events. One is destined for instance B, and the other for instance C in rapid succession. Once interface C receives that event, it performs some processing and then sends an event to instance B in the middle. In each case, the communication is from a sender to a single destination. Now for this diagram, the event for instance C arrives at instance B after B has performed an action that was triggered by the arrival of the event from instance A. What if instance A were to execute slower, or instance C responded sooner? Then the sequence diagram would change to look similar to this. Under the execution rules of xtUML, the two diagrams are equivalent. However, the order of events arriving at instance B has changed, and depending on the action blocks, could lead to two different behaviors. If architects and designers are not mindful of circumstances such as this, and neglect to intentionally include synchronization in their model, then these two diagrams could become an example of a race condition. As mentioned earlier, the arrival of an event drives the progression of time for an instance along its life cycle. For the destination, it doesn't matter if the event arrived from outside the component, from an instance within the same component, or from itself. Events originate as part of the actions performed by the sender. Actions are the fundamental increment of processing, and cannot be interrupted. From a time perspective, actions consume only local time, and when an event is exchanged between a sender and its destination, the transfer is considered instantaneous. Also, the time consumed by two different actions is not necessarily the same. Each of the actions supported by the xtUML action language can be categorized into the types of actions listed here. And within the structure of the xtUML model, actions can be placed within the states or transitions of a state machine, within the class operators or functions, and within component interface ports. In each of these locations, multiple actions can be collected into a block. Each of these blocks is called an activity. Each state or transition of a state machine is an example of an activity block, and when executed, an activity runs to completion before the next activity starts. For state machines, the execution rule associated with activities has been refined by convention. Although life cycles can contain activity in both the states and the transitions of the state machine, it has become convention that time advances only during the state activity. Consequently, state transitions are currently considered to be instantaneous, although that is not strictly stated in the rules of execution. When events arrive at the destination, they are first placed in an ordered queue. During execution, events are dequeued in the same order that they arrive, but not at a predictable rate. Once removed from the queue, the execution rule dictates that each event be identified as either a valid transition, an erroneous can't happen event, or is ignored, which is the default. This determination is based upon the name of the event, the current state of the state machine, and the contents of the state transition matrix. Execution then continues to the associated transition activity and then to the state activity if a valid transition is determined, or to another queue if the event is to be ignored. In the special case where the activity leads to a self-directed event, then that event is bumped to the front of the queue, and execution continues by processing it. This is the only circumstance when events are processed out of order. The last execution rule relates to interface messages. These messages provide intercomponent communication in the same way that events provide intra-component communication. Since the role of events and interface messages are similar, it's not surprising that their execution rules are also similar. In the case of interface messages, there is the potential for the port to contain activity, and the execution rule in this case is that the port activity must be executed before the message is directed to a destination queue. For many new modelers that have experience with simulation in other domains, the xtUML execution rules are a bit disquieting. The handling of action blocks and the progression of state machines in response to events is similar to the rules they found in these other domains. However, the relative nature of time in xtUML and the restriction on communication to sender-destination pairs, along with its associated synchronization challenges, creates many questions. In the remainder of this presentation, I'll try to answer some of the most common questions and provide some tips along the way. The most common question I receive is, how should I model delay if time is relative and only synchronized between the sender and destination instances? Some will try to experiment with coding various action blocks to directly implement the delay. However, this approach adds unnecessary states to the life cycle, and the processing performed during these timing states isn't useful. Further, this approach is sensitive to the relative scheduling of the transitions into and out of the action blocks. This leads to variability in the absolute timing of the delay. A better alternative is provided by the xtUML-Time entity. The time entity implements a bridge to the timer resources offered by the simulation platform. With its standardized set of access functions, modelers are able to schedule, in absolute time terms, delays for pre-existing events. Since the progression of time inside this entity is linked to the global simulation time, it is more reliable and ultimately leads to a more accurate model. Once this prescribed delay has expired, the event is then forwarded to the destination instance and placed in the appropriate event queue. At the top of the screen is an example of creating an event and then using the timeStart function within the time entity to delay the arrival of this event. As the example shows, implementing delayed events with this approach is easy. While discussing the concurrency rule for xtUML, I highlighted the challenge of maintaining synchronization when a message chain becomes longer than a simple sender-destination pair. Complex behaviors often contain these multi-step message chains, and they are not always easy to spot. Further compounding the challenge is human nature, where we tend to interpret an image, such as a sequence diagram, the same way each time we see it. Consequently, alternative interpretations, which may be inconsistent with the initial interpretation, become very hard to spot, and for designers, race conditions can appear. Three common circumstances where synchronization problems can appear are listed on the screen. In the first case, the sender fails to check that the destination exists and just sends out the event. If the destination is still to be created, then the event will be lost and the behavior broken. A similar variation of this problem occurs when the destination is not in the proper state to act on the event. This typically occurs when events arrive at the destination out of order, and the life cycle deviates from the intended path. To solve the missing destination problem is to recognize that this problem only occurs during the period prior to the destination being created. Often this is very early in the execution of the model, and there are two approaches available to avoid this race condition. The first approach is to include in the port action block of the destination component a test that confirms the existence of the destination instance, while the second approach is to perform all instance creation as the first stage of a component initialization. For the first option, this would lead to each destination port containing a snippet of action language that selects the destination instance and then takes appropriate action if the selection returns an empty result. The second option uses a similar snippet of code, but in this case it is placed in the action block launched by the simulator at the start of dynamic execution. This block is identified in the debug configuration associated with the simulation. Race conditions involving out-of-order events can be hard to track down. The symptoms of the problem are typically intermittent and can vary from run to run. When this type of race condition is suspected, it is good to review the state event matrix for the state machines that could be involved. If there are unassigned entries, then fill them in with either a suitable default or can't happen. Quite often these unassigned entries are involved in ignoring events and causing out-of-order sequences. To aid in debugging these problems is to employ the deterministic simulation mode of the simulator. Often to identify the cause of these failures requires rerunning the same test simulation several times. In this mode, the order of event selection is maintained from run to run. This predictability between runs makes the debug activity more effective. Later, when a proposed solution passes in deterministic mode, then switch back to non-deterministic simulation mode and rerun the test. A successful solution will pass the test in either simulation mode. Breakpoints are key to understanding the conditions that precede the failure. Since race conditions are tied to events, it's important to set breakpoints on both states and events that could be involved in the problem. This can lead to an excessive number of breakpoints to investigate. To reduce the number of false triggers, use the properties of each breakpoint to select only the conditions of interest. This will help filter out uninteresting breakpoint conditions and improve the quality of the debug effort. In summary, we have covered a number of topics related to time and the execution of xtUML models. As you develop your models, remember that all state machines execute concurrently, that the order can vary, and that message synchronization is only guaranteed for sender-receiver pairs. Consequently, designers must always be mindful of synchronization pitfalls and include explicit synchronization when necessary. Thank you for joining me, and remember that this episode is available at xtUML.org and at YouTube on the xtUML channel.